Hi everyone, David Packer here. In this video we will discuss how to fly from the Earth to Mars and back. And specifically we will focus on the major engine burns that are required and how much delta V we need for each of those. The goal of this video is to go over the calculations necessary to compute trajectories from Earth to Mars and back, and therefore help you with your planning of a Mars mission. Let's go ahead and begin by looking at the flight segments which involve engine burns. For the purposes of our mission planning, we will assume that our Martian spacecraft will be assembled in low Earth orbit using commercial launch vehicles to bring up the spacecraft components as well as any fuel and oxidizer that is needed. So our first flight segment involves flying from Earth's surface to low Earth orbit. And as we just said, this will be carried out by a bunch of commercial space launches. Once our spacecraft is assembled, it needs to be injected into Mars transfer orbit. That is, we need to take the spacecraft out of the low Earth orbit and inject it into Mars transfer orbit using a pretty big engine burn. Figuring out the delta V that we need to achieve here will be our first major obstacle. The spacecraft will cruise to Mars over the course of several months. Once the spacecraft reaches Mars, it needs to come out of the Mars transfer orbit and enter an orbit around Mars, preferably a low Mars orbit. For purposes of mission planning, we will assume that this can be done for free, that is without using up any fuel, but instead by changing velocity of the spacecraft using aerobraking, that is friction from the Mars atmosphere. At this point, let's take a moment to discuss how is it possible that a spaceship can use aerobraking to enter into Mars orbit. Right, there is some confusion here because the word braking indicates that the spaceship is slowing down. But with respect to the Sun, we know that Mars is traveling faster than the spaceship. So how can you possibly use aerobraking to slow down the spaceship into Mars orbit, whereas we know that the spaceship has to actually speed up? Well, let's take a look at this problem in more detail. We begin by plotting a little chunk of the orbit of Mars and also the orbit of the spaceship near the time of the encounter of the spaceship and Mars. And in this plot, both Mars and the spaceship are moving downwards. So when Mars is over here, where is the spaceship? Well, the spaceship is a little bit ahead of it. As they keep flying towards the encounter, both move downwards, but now we see that Mars is catching up to the spaceship. And finally, at the time of the encounter, Mars has completely caught up to the spaceship, and they're at the same point of space relative to the Sun. Well, here is the arrow indicating the velocity of Mars, and the arrow indicating the velocity of the spaceship. Let me label these as Vm for velocity of Mars, and VSS for velocity of spaceship. And clearly from this picture we can tell that velocity of Mars relative to the Sun is higher than velocity of the spaceship. So how can we make use of aerobraking in this situation? Now, to have a better understanding on what's going on, let's go ahead and transform ourselves to coordinates where Mars is at rest. That is, let's imagine that we are astronomers on the surface of Mars taking a look at what's going on. So here is our planet, and for us, the direction of motion of Mars around the Sun is going to be downwards. But because we're standing on the surface of Mars, Mars doesn't actually move. So now that we are in Martian coordinates, how does the spaceship move? Well, let's take a look at it. We are gaining on the spaceship, so the spaceship is coming to us from direction of travel of Mars around the Sun. Now, how fast does the spaceship appear to approach Mars? Well, let's call that VREL for relative velocity. Now, what is VREL? Well, it's just the velocity of the spaceship minus the velocity of Mars. right? In order to transform to coordinates where Mars is stationary, we have to subtract the velocity of Mars from all the other velocities. To recap, for observers on Mars, the spaceship appears to fly towards them, as indicated by the plot to the left. Now what happens during the encounter? Well, the Mars atmosphere slows down the spaceship, as indicated by the much shorter arrow on the spaceship which is right next to the planet. So from the point of view of an observer on Mars, there is nothing at all strange happening. The spaceship is flying towards Mars, and then it encounters Mars atmosphere and slows down and enters Mars orbit. However, what about an observer which is looking from the coordinates of the Sun? Well, in the Sun fixed coordinate, it appears that the Mars atmosphere, which is traveling at the same speed as Mars, drags the spacecraft along, making it speed up. And that is the process which allows the spacecraft to enter Mars orbit. That is, if on the plot to the upper left, the initial velocity of the spacecraft is indicated with a pink arrow, after the encounter with Mars atmosphere, the speed of the spacecraft relative to the Sun actually increases. So the new speed is higher than the old speed, and that is because the Martian atmosphere dragged the spacecraft along and made it fly faster. I hope that this little interlude helped us understand a bit better how it's possible to use aerobraking to make a spacecraft fly faster relative to the Sun. Right, and the main point here is aerobraking is with respect to the coordinates of the planet and not to coordinates of the Sun. In the coordinates of the Sun, because the atmosphere of Mars is moving much faster than the spaceship, it's not really so much aerobraking as aero pushing the spacecraft along to make it go faster. And now let's get back to our main task of figuring out the maneuvers the spacecraft needs to perform to fly between Earth and Mars. Our next goal is to take the spacecraft out of low Mars orbit and go ahead and land it on the surface of Mars. Now, for large spacecraft, usually a power descent is used because the Martian atmosphere is not very dense and it is hard to get enough friction from the Martian atmosphere to take the spacecraft all the way down to landing. However, we will again assume that we can do this maneuver for free using aerobraking, and that is mostly to simplify this part of the calculation. Once our spacecraft is on the surface of Mars, the astronauts are going to perform their exploration duties. But before the spacecraft leaves, there is an optional refueling. And in our case, we are always going to take this option, and that is because the total delta V to fly to Mars and back is kind of large, and we would need a multi-stage rocket otherwise. However, by refueling on the surface of Mars, we can just use a single-stage rocket, which is much simpler and also simplifies our calculations. As a side remark, you might ask yourselves, how did rocket fuel get to Mars in the first place? Well, there are two options. The rocket fuel could have been flown on a previous mission. However, there is an even more attractive alternative, and that is to make the rocket fuel in situ. For example, Martian water could be split into hydrogen and oxygen. Alternatively, the Martian water in combination with Martian carbon dioxide can be turned into oxygen and methane. By the way, this is one of the reasons that SpaceX is using methane for the next generation rocket engine, the Raptor engine. At the end of their stay on Mars, the spaceship needs to be launched from Mars surface and go into low Mars orbit. For the purposes of our mission planning, the delta V required to get to low Mars orbit can be simply estimated to be equal to the velocity of low Mars orbit at, say, an altitude of 100 kilometers. The next engine firing involves taking the spacecraft from low Mars orbit and injecting it into the Earth transfer orbit. This step is very similar to step 2, which we will discuss in greater detail later in the video. After the cruise to Earth, the spacecraft needs to enter low Earth orbit so that it can eventually land on Earth. In order to simplify our calculations, we will again assume that this maneuver can be done for free using aerobraking. Finally, the spacecraft needs to deorbit and land on Earth. Again, we will assume that this maneuver can be done for free using aerobraking. Indeed, all spacecraft that need to land on Earth use this strategy. They fire their rocket engine just slightly in order to make their orbit around the Earth intersect the Earth's atmosphere. The rest of the slowing down is done by aerobraking. For example, here is a landing sequence for the Soyuz spacecraft. It begins with a deorbit burn, in which the spacecraft changes its velocity by 128 meters per second. Following the deorbit burn, the spacecraft cruises for a while, as the lowest point in the trajectory happens on the other side of the Earth. Right before the spacecraft reaches the upper atmosphere, the descent module of the Soyuz splits away from the habitation module and the service module. As the descent module with the astronauts on board reaches the upper atmosphere, it starts to slow down. Indeed, the friction between the atmosphere and the spacecraft causes a fireball to surround the spacecraft, as can be seen in this image from inside the descent module. As the spacecraft continues to slow down, eventually it deploys a parachute, and finally, just before touching down on land, it fires a set of rockets to cushion the touchdown point. Presumably, our spacecraft traveling to Mars would utilize a similar system for landing both on Mars and on Earth. Compared to the Soyuz, our spacecraft would need two modifications for its landing sequence. First, especially when we land on Mars, we don't really want to break our spacecraft into three parts. We want to land the entire spacecraft. Second, just like the Soyuz, our spaceship will use friction with the atmosphere to slow itself down. However, the final landing will probably be done using a propulsive technique, that is, a brief firing of the rocket engine, to completely slow down the spacecraft and bring it to a stop, as opposed to using a parachute. There are two main reasons to prefer a powered landing. First, a powered landing gives much more precision, so you can choose your exact landing spot. Second, the air density on Mars is really not high enough to utilize a parachute to bring the spacecraft down to a complete stop. The delta V required for a powered landing is actually not so large, and we will completely ignore it in our calculations. Now let's discuss the strategies for figuring out the various propulsive maneuvers. For the first maneuver, from the Earth's surface to low Earth orbit, we need to figure out how much mass we can put into space using commercial launch vehicles. And this is pretty straightforward. We just look this up on the web. We can look up the cost as well as the lifting capacity of the available commercial launchers and just use those facts. Almost certainly just a single launch will be insufficient, so you will have to use multiple launches to put the entire mass of your spacecraft into low Earth orbit. Injecting the spacecraft into a transfer orbit requires a bit more thought. So for maneuver number 2 and maneuver number 6, we need to do a similar kind of calculation, and that will be the main topic that we will discuss in the remainder of the video. We will take a two-step approach. First, we will use a pork chop plot to read off how much we need to increase the speed of the spacecraft relative to the speed of the Earth around the Sun in order to put it into the transfer trajectory. And second, we will perform a calculation to get that spacecraft velocity starting from low Earth orbit. And don't worry, we will go through all these details step by step. Finally, we need to be able to calculate the delta V required to get to to low Mars orbit, starting from the surface of Mars. And for here we just make an estimate. We use Mars orbital velocity to get the delta V. Alright, let's discuss these pork chop plots and delta V calculations. Our goal is to find delta V that is required to inject the spaceship into the transfer orbit, starting from a low planetary orbit, like low Earth orbit. It turns out that just like in comedy, timing is also very important in space flight. So the question is, where should Mars be when we launch our spacecraft from Earth in order to minimize the delta V requirement? Well, the most efficient trajectory is a Hoffman transfer. That is an ellipse which just kisses the orbit of Earth and the orbit of Mars. In order for the spacecraft to meet up with Mars when it reaches Mars orbit, what do we have to do? We have to have Mars slightly leading the Earth. So as the spacecraft is flying, Mars also moves, and the spacecraft and Mars meet up on the other side of the Sun. That is, the position of Mars relative to the Earth has to be just right, so that the spacecraft and Mars can meet each other on the other side. We don't want Mars too far ahead, because then the spacecraft will miss, right? And we will need to add more delta V in order for the spacecraft to be able to intersect Mars trajectory. So here I have Mars a bit ahead. It's going to be a bit ahead on the other side of the Sun as well, after the spacecraft finishes cruise, and we will have to modify the spacecraft trajectory, which will require higher delta V. Similarly, we don't want Mars to be too far behind. So let me draw the case where Mars is too far behind with pink. And again, you see here, Mars and the spacecraft don't meet up nicely on the other side of the Sun. In order to make them meet up, we again have to modify the trajectory, which again requires more delta V. Now, because it takes Mars longer to go around the Sun once than the Earth, the optimal alignment of the two planets doesn't happen all the time. It happens roughly once every 2 years. The pork chop plot is a tool that helps us decide when the optimal alignment between Mars and Earth occurs, and therefore it helps us decide when to launch our mission and how much delta V we are going to require. So let's go ahead and schematically take a look at what a pork chop plot does, and then we are going to go to a website which generates pork chop plots for us. So we are going to have two axes. The vertical axis is going to be the flight time. That is how long after launch from the first planet until we reach the second planet. The horizontal axis will be the launch date. That is when we are launching our spacecraft on its transfer orbit. Now the pork chop plot will consist of a set of different colored contours. These contours will be quasi-periodic. That is, they will occur at regular intervals, but the contours will not be completely identical. So what does the color of the contour indicate? The color indicates how much V infinity is required in order to inject the spacecraft into the transfer orbit. And as we will see later, V infinity is related to delta V. How much delta V we need in order to take the spacecraft out of low planetary orbit and inject it onto the transfer orbit. Now, V infinity and delta V are related. The larger the V infinity, the larger the delta V requirement. So if we want to minimize delta V requirement, we should minimize V infinity, which is what is plotted with color in these pork chop plots. Now the two arrows show optimal flights in terms of delta V or in terms of V infinity. That is, they point to blue regions, which are the regions in which V infinity is smallest. Now, why is the pork-chop plot called a pork-chop plot? Well, it's because these optimal trajectories come in pairs, and these pairs look like pork chops to some people. Why do the two regions of minimum V infinity come in pairs? Well, the lower part of the pair, the one with shorter flight time, corresponds to the direct trajectory to the planet, while the upper part of the pair corresponds to the trajectory where we fly past the planet and then come back to it, just like indicated with the green line in the schematic of orbits above. That is, the direct trajectory corresponds to the black line, and the out and back trajectory to the green line. Surprisingly, it turns out that both trajectories have approximately the same V infinity and hence delta V requirements. Now, how often do these pork chop repeat? Well, they repeat whenever Earth and Mars come into alignment. That means they repeat approximately every 2 years. Now, how should we pick the launch date? Well, we have two criteria. First, we want to pick a launch date that corresponds to a small V infinity and therefore a small delta V requirement. Second, we want to pick a launch date which corresponds to as short a flight time as practical. And the reason for this is the shorter the flight, the less consumables the astronauts will use up, and the less they will be exposed to radiation of space. Okay, let's go ahead and take a look at how to generate pork chop plots. So the Space Dynamics group at the Polytechnic University of Madrid has this nice web page which generates pork chop plots for you. Now let's see how this works. You need to specify a couple things. You need to specify a range of departure dates and a range of times of flight. So because this is an example, I'm going to choose a departure date in the past. I'm going to choose the default one from 2015 to 2019. When you actually are writing the essay, you should choose a departure date in the future, which would allow your spacecraft time to be constructed and launched to Mars. Now for time of flight, since we're flying from Earth to Mars, somewhere between 100 and 1,000 days is perfectly reasonable. Our departure body is the Earth, and our arrival body is Mars. And for planning the trip back, you should switch them. So when you're planning the trip back, you should select Mars as your departure body and Earth as your arrival body. Okay, let's go ahead and plan the trip from Earth to Mars. Having specified these parameters, we're going to hit departure V infinity. And this guy is going to construct the pork chop plots for us. So here is our pork chop plot. On this axis is plotted the departure date. And on this axis is plotted the time of flight in days. So here is the start of 2015, January 1st. And let's see, this is 6/10 of the way through 2016. So the end of 2015 is somewhere around here. Now, what does the color mean? The color is the V infinity, which is required for departure. So if we scan our mouse over the colors, we can tell it can tell us what is V infinity. So for example, right here, this is a region with very blue color, and it tells us that delta V, it really means delta V infinity, is 2.99 kilometers per second. Right? That is how much faster the spacecraft has to go in orbit around the Sun than the Earth does. We are going to take this number, the 2.99, and use it to calculate delta V from low Earth orbit. Specifically, our goal is to take V infinity from the pork chop and convert it into a delta V, which is necessary starting from low Earth orbit. The pork chop plot doesn't know anything about the spacecraft's trajectory around the Earth. It only knows about orbits around the Sun. And therefore we need to supplement the data from the pork chop plot with data about the spacecraft's initial orbit around the Earth, or around Mars if it's departing from Mars. Figuring out how to do that will be the point of the second part of this video, which will appear as a separate video. I hope you enjoyed watching it thus far, and remember to stay curious.